Good evening, all. Welcome to course ME78 Thermodynamics Lecture 4 of NPTEL. I'm Priyanka Rajeev. I'm a student of Mechanical Engineering Department of IIT Kanpur. Today we will be seeing week 3 revision questions and week 3 assignment questions, which are based on first law of thermodynamics. So these are the revision questions. First question is, a person wrote the statement of the first law as dq equals dw plus delta E. Why is it wrong? Okay, so here, as we know, the most common method by using sign convention and all, you have to write this sentence as, okay, I'll just copy this question and write it over here. Okay, so this is the question. So the answer should be, the correct form of first law of thermodynamics is del Q or dQ minus delta W equal to dE. So internal energy of a substance or material is a measure, it can be quantified using temperature of that substance, etc. So those properties, using those properties, we are measuring, we are getting an idea of what is the internal energy of that material. And that internal energy of that material changes with the heat supplied, changes with the heat taken away, or changes with the work done on the system or by the system. Okay, so sign convention usually, uh, this dE is the total energy, right? This is the total energy, and it is often taken as like kinetic energy plus potential energy, right? And when we are writing this dq equal to dw plus de, what happens is there is a mix up of this sign convention is happening. So this is the non-standard way, because mix up of sign convention is happening. Okay, now so the net heat of added to the system should be balanced by change in internal energy plus any work that is done by the system or done to the system. Okay, uh, so that is why it is incorrect. So it is with respect to the consistent sign convention that is typically used in thermodynamics, this form which is given in the question is wrong. You have to follow the convention that I have shown here. Okay, now next question. Okay, this is about nozzle. So nozzle, what does the what does the process occurring in nozzle accomplish? That is the question. Okay, 1 second. Okay, this question. So nozzle is a steady flow device. So nozzle, steady flow device. Okay, it is used for uh, increasing the velocity of the flow at the expense of fluid pressure. Increasing fluid velocity at the expense of fluid pressure. Okay, so in thermodynamic terms, nozzle is a device that converts nozzle converts enthalpy. So it is like it 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 may include pressure head also into kinetic energy. Okay, so this is what is happening. So enthalpy to kinetic energy. So that is what is increasing the velocity of flow at the exit of the nozzle. Okay. So usually nozzle, when we are thinking about uh, in an ideal scenario, heat transfer in nozzle is often neglected, and changes in potential energy etc. are also neglected. Okay, only change is like the major changes in kinetic energy. So kinetic energy change is the dominant one. Change is dominant in um, nozzle across the nozzle flow, and it is coming at an expense of fluid's enthalpy. Okay, now next question is, okay, okay, wait, okay. So for conservation of mass to be applied, the system must be in a steady state process. Is this statement correct? Okay, it comes over here. Conservation of mass to be applied, the system must be in a steady state process. Is this statement correct? Mm, uh, Obviously not. So conservation of mass is a universal law. Okay, so it can be um, applied to any kind of system like steady or unsteady processes. It can be applied for steady process. What will happen is rate of change of mass in the system will be 0. Okay, there won't be change in mass. So dm by dt equal to 0 when it comes to uh, you know so the whole continuity equation I'll write. So dm by dt of for example, if we are taking control volume, so equal to m dot in minus m dot out. That is the conventional I mean continuity law, right? So continuity equation is given by this. Now they are saying, so for steady state what will happen, the change in this mass of control volume with respect to time will be 0. So it will be like whatever is entering the system is going to leave the system. So that is the only change that is happening when it is steady state. Unsteady state means you have to solve this entire equation to find the mass of the control volume at any instant of time. So conservation of mass or continuity equation is applicable to all the system. Now next question. Okay. Next up is what is the difference between flow work and shaft work? Okay, that is a very easy question, direct questions. So I am solving this in order to revise the concepts. Okay, so instead of taking the entire theory, I was thinking I'll solve the question and discuss the theory along with that. Okay, so flow work means what? Flow work means if you consider a volume element V. Okay, so volume V of fluid, if we have to push this mass or this volume in and out of control volume, then we will be taking that fluid energy that is associated with this pushing of mass into and out of the control volume as flow work. So that so flow work or flow energy, both are the same term. So this, with this work or energy, um, is that is associated with pushing this mass into or out of the control volume. So it can be denoted by, if there is a pressure, that is like pressure of the system, that system is having P pressure, then flow work will be equal to PV. Okay, so in a steady state, steady flow device, when fluid crosses the boundary, the system either does work on the fluid, or work has been done by the fluid simply by virtue of pushing fluid across the boundary. So this is the system, and there is a fluid element, crossing this boundary. So either the system is doing work on the fluid element, or fluid element is doing the work on the system. So this PV can be either positive or negative. Okay. Then shaft work means what? This is V. Okay. Shaft. So shaft work, in the other hand, is a mechanical work. Okay. Um, it is like when you think of the scenarios of rotating shafts, stirring. Okay, rotating shaft, uh, then stirring process, like in mixing and all those things, we will be stirring the mixture. So that stirring process, then uh, when we think about like alternators and generators and all this mechanical work is called, um, if you are using like mechanical means to transfer energy or work, that is called shaft work. Okay, so mechanical means of transferring energy, so that is shaft work. So flow work and shaft work, I guess the difference is explained well. Now next question, do you agree with the statement that first law analysis can be performed only if the processes are reversible? Sorry, processes are reversible. Let's see. Okay, so that didn't work. Hmm. Over here. Okay. Uh, so the answer is no. First law analysis can be done for both reversible first law applicable for both reversible and irreversible process, reversible and irreversible processes. Okay. Um, okay. So why first law is actually what? Conservation of energy, right? So conservation of energy, or first law, just like when we were discussing about mass conservation law, conservation of energy is a universal law, is a universal law. So what is happening is irreversible processes might have some frictional losses or heat dissipation, which is like cannot be recovered by the system again. Okay, so when we have to reverse the state of the system, we cannot recover the heat that was dissipated due to frictional loss and other like if it is an electrical system, then resistance due to joules heating, heat might be dissipated. So these cases we cannot recover it back. But if you see, the energy which was there in the system was like you can account each of the loss term to some phenomena, and you can calculate like, okay, the whatever loss was there, and whatever the energy is remaining in the system when you mm, you know add all those terms together, then we will be getting the initial energy. So it is like conservation of energy is applied. So whatever dissipation is happening, that is in uh, connect or that is in accordance with the first law of thermodynamics. So no violation of that law is happening. Okay. Now next question. A substance is heated in a closed vessel. The heat transferred per unit mass of substance will be changed in the specific internal energy of the substance and not in the change in the specific enthalpy between final and initial states. Is this always true? Okay. So the answer will be like, for a closed system where this no mass is crossing the boundary and there is a constant volume, and if there is no flow work term is there, then changes in enthalpy are not directly relevant for heat transfer. Okay. But this delta U or change in internal energy is showing, or it is a term that is uh, showing the energy change. So therefore, if the volume does not change, and if there is no other kind of work such as boundary work from a moving piston or anything, so heat added equals the change in internal energy. Okay. So in general, in a sealed container, dq equal to du. Okay. So for but if there is a closed vessel which is having a moving piston, closed plus moving piston, then you have to consider the delta H also, like U plus PV. Delta H is what? Like already internal energy will be there, and then flow work will also be considered. Okay. So, sorry, D of U plus PV. Okay. Now, so the statement is uh, strictly true only if no boundary work is done. Okay. So they were saying change in specific internal energy of the substance, and so heat transferred is only changing the specific energy of the substance and not any change in specific enthalpy. But I'm saying that delta H has got this du term. So if no boundary work is done, then delta H and delta U will be having the same change. Okay. Then question number 7. In a steady state, steady flow process, which of the following are essential? Each flow rate does not change with time. Specific enthalpy of inflows, outflows does not change with time. Specific internal energy of the system does not change with time. Specific volume of system must not change. The specific enthalpy of the substance should be same everywhere in the system. Okay, I'll explain one by one. Okay. So it is like each flow rate does not change with time. So mass flow rates at each inlet and outlet remain constant with time. So yeah, that should be there. Like whatever. Uh, uh, for steady state process, we need a steady mass flow rate at the inlet and outlet also. So each flow rate does not change with time is essential. So this holds. This is required. Then specific enthalpy of inflows, outflows does not change with time. Specific enthalpy of inflows, outflows, if we are saying we need all the properties at every location to be constant in steady state. So if specific enthalpy at inlet does not change with time, or specific enthalpy of outlet does not change with time, then this idea of properties not changing with time or location in steady state flow is um, is holding, right. So I think B is also very essential. Then there is next statement is specific internal energy of the system does not change with time. Again, specific internal energy is also a property within the control volume. So if it is not changing with time, so that is uh, again steady state process. uh, and uh, but if it is like locally varying, I think we have to check for an average or the entire control volume. When we average it out, if this is constant, that is also okay with it. So it is not about spatial variation, but only with time variation we are talking about. So this is also essential. Then specific volume of system must not change. uh, okay, so specific volume of the system, spatial variation will be there, but even if like if there is a requirement that the system's volume or specific volume not change, um, as long as everything is changing in a steady fashion, then there is no such particular requirement is needed. Then so if so this is not an essential point. Okay. Then the next thing is, so why I'm not saying this is, it is not said anything with time. Okay, specific volume of system must not change. We cannot say that. There will be local variation and all, but with time, yeah, it will be constant. Then next is specific enthalpy of the substance should be same everywhere in the system. uh, that is also not required because in heat exchangers, there will be inlet and outlet enthalpies are different. So and still they are like steady state. So that is also not required. Then there should be no change in potential energy. Again, potential energy, kinetic energy, if it is mm, if there is no change at all, uh, that is also not a specific requirement for steady state, because in many devices like turbine or nozzle, KE and PE, they are I mean change in kinetic energy and potential energy, they are small. uh, they are not strictly zero. Okay, like change will be there, and still it will be a steady state process. So kinetic energy, potential energy change, that doesn't matter. Then we have got inlet and outlet state should be same as one another. uh, that is also not required, because uh, so if you're seeing air conditioning device, so the inlet will be having one state, outlet will be having another state, but it is a steady state process. Then finally, steam should be the working substance. uh, no, it can be any working substance. Like when I was talking about air conditioning device, there will be coolants. Coolants are different substances, right? So there also, it is not a essential I mean criteria. Yeah, so only A, B, C is there. Then eighth question, uh, consider two definitions of systems for an operating refrigerator with closed door. System A includes the entire body, and the system B is only the air inside the refrigerator. In which case will there be work transfer? Okay. Uh, so system A is this entire refrigerator, and system B is just the air inside. So we are defining two different systems with the different system boundary definitions. Okay. Uh, so just by system boundary definition, we can observe two different things. Okay, some phenomena will be included in the system, some phenomena won't be. Okay, so system A, when we are thinking, it's the entire refrigerator. Entire refrigerator will be what? Like there will be compressor. Okay, compressor, then expansion valve, then coils will be there, right? Coils, etc. Uh, then these are all inside the system boundary when we are thinking about the entire fridge. So the only energy exchange with surroundings will be only electrical energy input. Okay, because all the heat exchangers and everything is inside the system itself. I was talking about it before also. So work and energy is boundary phenomena. So whatever is happening inside the boundary, if it is not crossing the boundary, the heat, so there is heat exchange happening at the coil. There is work input given to compressor. There is heat output going from different devices, sorry, different modules of refrigerator. But as long as those are all inside the boundary or outside the boundary, we don't care. But when you are defining the system boundary such that it crosses that heat flux path, or the heat flux is happening, flux means what, like it is crossing the boundary. So that system boundary, if this heat and work is crossing, then only we can observe or compute those observation into our calculation. Okay, so here only electrical energy input is there, uh, that is given to the compressor, uh, but and there will be shaft work or flow work, everything which is inside the system we are not considering at all. But when we are thinking about just the air inside, then uh, okay, then the fan inside the refrigerator is doing work on the air. Um, so that is, there we are seeing the shaft work. Okay, so that is a difference. So in one system we cannot observe the shaft work, the other system we can observe the shaft work. So system A, it looks like only electrical energy is crossing the boundary, uh, and mechanical work is not there. And in system B, you can see that the shaft work, so the boundary of the air system is showing that work transferred to the air also. Okay. Now next up is water flows through. Okay, water flows through a heater in steady state at 1 kilogram per second and undergoes a temperature rise of 50 Kelvin. Uh, Inlet velocity is 1 meter per second and outlet velocity is 1.5 meter per second, and there is an elevation increase of 1 meter. Show that in the conservation of energy equation for a steady state flow process, the changes in Ke and Pe, kinetic energy and potential energy, are very small in comparison to the change in specific enthalpy. Okay. I'll take it to the next page. Okay. So the question is, for water with a temperature rise of 50 Kelvin, delta T equal to 50 Kelvin, enthalpy change we have to find. Okay. So enthalpy change will be what? Cp delta T, right? Cp delta T. So Cp for water is around 4.2 kilojoule per kilogram Kelvin. Okay, so if you use that and delta T, we will be getting 4.2 times kilojoule. So 10 to the power 3 times 50 equal to 2.1 times 10 to the power 5 joule per kilogram. Okay, so that is the change in enthalpy. Now, change in kinetic energy per unit mass. The delta Ke equal to, so inlet velocity and outlet velocities are given. So we can just, you're just taking the head of it. So mass is not required. V out square minus V in square by 2 equal to 1.5 square minus 1 square by 2 equal to 2.25 minus 1. 1.25 by 2 equal to 0.625 joule per kilogram. So that is lesser than this value, right? Delta H value. Okay. And change in potential energy equal to again mgz delta z. We will be just taking g delta z. So delta z is what? Increase in elevation is 1 meter. Okay, so it is 9.81 times 1 equal to 9.81 joule per kilogram, which is also very small compared to this 10 to the power 5 joule per kilogram. So delta Ke and delta P are negligible compared to a large enthalpy change of liquid water when it is heated by there is a difference of just 50 Kelvin. Okay, and that is what is creating this much big of a enthalpy change. Okay, so you can just compare the magnitudes. That's it. Next question, question number 10. Okay. For a steady state flow process in a nozzle or diffuser, it is wrong to say the change in kinetic energy is negligible, but okay to say that change in potential energy is 0. Why? Okay, so here itself I'll explain. It is wrong to say that change in kinetic energy is negligible, but okay to say that change in potential energy is 0. Okay, so in a nozzle or diffuser, as we have seen earlier, nozzle, the primary focus of nozzle is to increase the fluid velocity at the expense of enthalpy. Okay, diffuser also the same way. It is like to change the velocity only. So, so the delta Ke value will be very high. Okay, so that is not definitely negligible. But Ke and Pe, most of the time, the head difference will be very, when pressure head difference, sorry, not pressure head, the elevation that is happening will be very small. So delta Pe is almost 0 in those cases. So delta Ke is the main term. So why it is associated with the application of this device. The nozzle and diffuser is used to change the velocity of the fluid. It's not about increasing the potential energy. It is not some kind of a dam or something. So that is why Ke, if you are neglecting, then you are neglecting the application. You cannot say that, right? The term is really high, so you cannot you can never say that okay, you can neglect this thing. Okay, so next up is cylinder piston. Okay, in a cylinder piston arrangement, a substance is heated and the piston okay, and the piston is moves against a force and does work. For a given heat input, does the work output depend on the substance in the system? Okay. Okay, so that is as we have seen in the previous lectures, one question. It is like you are heating up a substance inside the cylinder piston arrangement, and that heat is expanding the substance, and then it is pushing the piston outwards, and that is the force. Uh, Force was given by the expansion of the system, uh, expansion of the substance inside the system, and that was moving the piston. That was the work, right? The movement, the displacement of the piston that has happened because of the force um, given by this expansion of the substance was the work that we were calculating over there. So here they're asking for heat input, for a given heat input. If we are changing the substance, then will the work output be changing? So the thing is yes, because as we have seen, the expansion is what is causing this work to happen, or the force is provided by this expansion only. So if the material is changing, it will have different specific heat, or um, the process path will be different, or phase behavior will be different. Sometimes it will be evaporating really high. I mean, evaporation rate will be really high. Sometimes it is very low. Specific energy, sometimes it will absorb the energy like real fast. Sometimes it will be very slow to, absorb the energy. So these material properties will depend on the force that is being provided to the piston. So yes, definitely it will change. Okay. So yes, substance determines work output. De Substance determine work output with the heat input. Okay. Okay. This is UF is unsteady uniform flow. Okay, unsteady state uniform flow. So in a unsteady state uniform flow process, formulation or analysis, which of the following must not change during the process: mass flow rate, specific enthalpy flows, specific internal energy of flows, or state within the control volume with time. So uniform flow means what? So uniform flow means it is like throughout the system, it is in the same state. Okay, whether it is inlet or outlet or in between, it is all the flow stream is uniform in state. That means no property is changing with the location or spatial variation. Then unsteady state means what? The properties can change with time. Okay, so mass flow rate can change with time in unsteady state and uniform flow. uh, that means like mass flow rate means with respect to time, mass flow is changing. So yes, that might happen in unsteady state process. Then specific enthalpy of the flow can also change in time if the inlet or outlet conditions vary, so that is also there. Then specific internal energy of the flow. uh, so specific internal energy is not particular about steady state or unsteady state or uniform flow or steady flow. That is not, it is not particular to this kind of approach. So if flow is like uniform at the inlet, then it has a uniform property at the boundary at any moment. Okay, any time. But it can vary with time if there is an unsteady scenario. And then there is this state within the control volume with time. So state within the control volume with time definitely can change, because state is determined by properties change with time in unsteady process. So yes, that is there. So in unsteady uniform flow analysis, we can assume that at each instant fluid entering or exiting as a uniform property, but that property can change from time to time. So at a given instant of time, at every location, the properties will be constant. But if you take the next instant of time, that constant properties will be different value, but it will be same throughout the spatial location. Okay. So all this thing, it is not necessary that it will remain constant throughout the time, but for the since it is written uniform, spatial variations like at individual local location, that is not uh, will not be there. Okay. Next is an adiabatic cylinder piston arrangement contains a substance which is compressed to half its initial value. Comment on the validity of the statement. The internal energy change of the substance will be same for every working substance. Okay. So adiabatic means delta Q equal to 0. Contains a substance which is compressed to half its initial value. So whatever work that was done in compressing has transferred to the internal energy change of the substance. Okay, this is like, but uh, okay. And another thing is, it depends on the uh, if the working substance. Okay, uh, what they are saying is, so since it's a adiabatic system, delta Q equals to 0. So W, according to first law, the work done is going to be change in internal energy. So this is for one particular working substance, that is going to be same. Yes, this holds for any substance, but the change in internal energy won't be same for every substance, because there are intrinsic properties of the substance that is going to um, like take this internal energy in different manner. For example, if there is this density, like high density and low density substances are there, so compression work will be different for different substance. For example, if there is a low density substance, so if you have to put in a lot of work for compressing the same amount of volume. So for a given uh, what to say, for a given work magnitude of compression, uh, the low density substance will not be having that much of internal energy change, because it won't be getting like the compression won't be that much evident in a lower density uh, substance. But in a high density substance, it might it might increase really high in when we are trying to quantify internal energy change. So yes, it depends on the working substance. The internal energy change of the substance will be same for, no, not same for. Okay, so it is false, this statement is false. It is not same for uh, every substance, every working substance. Next is, a well insulated vessel contains tap water into which a cube of ice is dropped. The vessel is closed and is well insulated. The process inside the vessel can be characterized as isobaric, isochoric, isointernal energy, isenthalpic. So well insulated and closed, that means there is no heat and mass exchange with surrounding. Pressure inside may or may not be constant, because water plus ice system might might be at like nearly constant pressure uh, if the vessel is not rigid. But if it is like very very much sealed and uh, rigid, then pressure could vary slightly, because of uh, the heat exchange that is happening between ice and water. There will be a melting of ice will be happening, so that volume change will be happening, because ice has got different density, water has got different density. So because of that, there is a like density change is happening, and because of that volume change will happen, so the pressure will be varying. So that will be there. So we cannot definitely label it isobaric unless we know the vessel is a bit of flexible or rigid. Okay. Uh, Now, next is, if the volume of the water plus ice is basically the volume of the container, and container's volume does not change, then it can be considered isochoric. But just like how I said, ice has got a different density. So the volume when it melts and volume when it was solid, it is not the same, right? So there is a slight change when while the ice is getting melted inside, then it is definitely going to cause a change in volume. Again, it is up to our application. We have to consider whether it is like acceptable as isochoric or not. Okay, so if we are okay with a small volume change, and that is like coming into in the tolerance level of our system that we are considering, then it can be taken as an isochoric process. If not, like ideally, if we are seeing, it is not, because there will be a slight volume change. Now, next is isointernal energy. Okay. So, vessel is well insulated. So, there is no heat input from outside, and it is closed also. So, there is no mass flow in or mass flow out. So, total energy of the system is supposed to be constant. So, yes, so isointernal energy is like uh, is there. So, this is an isointernal energy process. Then we have got something called isoenthalpic. So, isenthalpic process. Uh, so, when ice is melting and when ice is warming, then it is not necessarily isenthalpic. Okay. So, enthalpy change can happen with phase change. So, yes, it is not isenthalpic, because again, I was saying, if it is not isochoric, then delta V can cause enthalpy change. So, that is there. So, isointernal energy is correct. Isochoric might be if and A and D and B cannot be guaranteed. Okay. Then 3.15, this is the last question of revision question. How is the flow work accounted in the first law equation for a control volume? What type of work are to be included in the work term? 1 second. Just okay. How is the flow work accounted in the first law equation for a control volume? What type of work are to be included in the work term? Okay. So, flow work control volume analysis, we will be taking the total energy term as this H plus V square by 2 is the kinetic energy plus potential energy at inlet and outlet. Okay. Yeah. So, this H will be having what? U plus PV, right? So, PV is the flow work term here. Okay. So, in control volume analysis, yes, we take flow work into account. All other work forms, all other like work crossing the boundary or the boundary work is also included in the work term. Yes, so this is there. So how is the flow work accounted in first law of equation for a control volume? That is included in the enthalpy term. So that is the answer. Yep. So these are the assignment questions. First is a gas enters a turbine at pressure phi1 or phi1 bar and temperature theta 1 degree centigrade. Two independent properties. Okay, pressure and temperatures are independent properties only. And expands to pressure phi2 bar and temperature theta 2 degree centigrade. The specific internal energy at state 1 and state 2, U1 and U2 respectively. Write the expression for specific work of the turbine. Okay. So first law for turbine is as follows. It is Q dot minus W dot turbine equal to M dot H2 minus H1. Okay. So this is like we are taking steady state steady flow approach for turbine. And so that is why kinetic energy, potential energy is like neglected because it is not stated explicitly that this is there. The first law is like this, and H1 and H2 can be written as U plus PV value. And if you want specific work, then it can all be divided by m dot. Okay. Now, enthalpy difference we have to calculate, H2 minus H1. So H2 minus H1 is going to be U2 minus U1 plus P2 V2 minus P1 V1. Right. Okay. Mostly turbine processes, we are not considering heat work over there, so it can be taken as 0 also. Then it will be like W turbine equal to m dot H2 minus H1. Okay. So the final expression will be W turbine equal to W turbine equal to U2 minus U1 times plus P2 V2 minus P1 V1. Or if you want, you can, instead of P2 you have to write Phi2, and instead of P1 you have to write Phi1, and temperature you can write it as CVT. Okay, CV. So U2 equal to CV theta 2, U1 equal to CV theta 1, then P2 equal to Phi2, and P1 equal to P1. That's it. But you don't need to compute this one because U1 and U2 is directly given as specific internal energy. Yeah, so that is the answer. Second question. Steam flows into a straight pipe, and after some distance there is a contraction in the pipe followed by another straight pipe. At inlet to the contraction, the pressure is Phi1 bar, temperature is theta 1 degree centigrade, and velocity is V1 meter per second. The inlet and outlet pipe inside diameters are D1 and D2 millimeters respectively. The outlet pressure is Phi2 bar, which is less than Phi1. The process can be considered to be reversible and there is no heat transfer to the surrounding. Write the expression for the velocity at the exit. Okay. So steam is okay. So we will be first writing the conservation of mass equation at for this steady state steady flow process. So m dot equal to rho 1 a1 v1, and since it's steady state, it will be rho 1 a2 v2. Okay. Inlet and outlet will be mass flow rate at inlet and outlet will be equal, and this a1 a2 everything can be written in terms of d1. So it is like a1 equal to pi t1 square by 4, and a2 equal to pi t2 square by 4. Apply first law, reversible, adiabatic, isentropic, everything is given. Reversible, no heat transfer, adiabatic. Okay. So then if that is the case, then H1 plus V1 square by 2 equal to H2 plus V2 square by 2. Okay, that is the first law for such a system because Q equal to 0, W equal to 0. Now, H1, we can write it in terms of Phi1, theta 1, Phi2, theta 2. And since it is isentropic, theta 2 can be found from steam tables or from isentropic relations. Okay, then we can solve for V2. So how to solve for V2? V2 equal to root of 2h1 minus h2 plus v1 square. Then from continuity we can find rho 2 to find v2. Okay, you have to find rho 2 and in order to find v2. Then yeah, so that is the velocity v2 we have to find. So this is like you have to rearrange this thing. Okay, that's about it. Then question number 3. A liquid at temperature theta 1 degree centigrade and pressure phi 1 enters a pump where its pressure is increased to phi 2 bar. If the flow rate is m dot kilogram per second, then what is the power input to the pump? Okay, so this is also a steady state, steady flow process. Control volume which we are observing is the pump. So first law, we will be ignoring kinetic energy change, potential energy change and everything. It will be going like this. Just heat input or heat work, the difference between them is going to be the enthalpy change of the system. If we are assuming this is adiabatic, because temperature change is not said anywhere. Okay, so for pump generally we will be assuming it is adiabatic, only the shaft work we will be considering. So W equal to m dot h2 minus h1. Incompressible liquid h2 minus h1 will be m dot v incompressible, so volume will be constant, phi 2 minus phi 1. Okay, so this will be the expression for the flow work. Next question. CNG is being filled in a cylinder through a tube where the pressure is phi 1 bar and temperature is theta 1 degree centigrade. That is ambient. Before filling starts, the cylinder is fully evacuated. After some filling, the mass of CNG in the cylinder is mng kilogram. Write the two independent properties at this stage of filling. Okay, so system is that cylinder where we are filling natural gas, and after partial filling, okay, state of the cylinder or the properties inside the cylinder, we can say that it is pressure and temperature. Okay, so we can say pressure and temperature because one is from compressed state. You can you are pouring it into the cylinder, that is going to expand a bit. So because of expansion, again what we call it as Joule's effect, it will be temperature will be like lowering, so temperature changes also there. Because the question states that mass is like mng, and we know the filling conditions like phi 1 and theta 1. We need to know like pressure and temperature inside the cylinder, like final one after filling. So that is why we can say that these are the two independent properties of the stage of filling. Okay, now fifth question. Consider water flowing through a tube of a solar collector. The tube external diameter and length are dt and lt respectively. It is given in meters. Water enters the tube at temperature theta inlet in degree centigrade, and its mass flow rate is m dot kilogram per second. the net heat transfer rate through the exterior wall of the tube, where the incident solar radiation less losses to ambient, is B solar watt per meter square. So power per area that is given. So heat transfer per area. Fine. Water inlet and outlet pressures are equal and approximately equal to ambient pressure. How can the exit temperature of water, theta out degree centigrade, can be calculated? Okay, so the control volume is the tube with water flowing through it, and it is to be taken as steady state SSSF process, and mass flow rate is constant. So energy balance is going to be what, like, we are only considering the heat transfer. So q dot equal to m dot h of outlet minus h of inlet. Okay, so if pressure is constant, then h delta h can be written as cp delta t. Okay, t out minus t in, or the theta out minus theta in, right? Like this, theta out minus theta in. Okay, so q net, how to calculate q net, or the q dot is B solar, that is given in watt per meter square, times the area exposed, or area of tube surface. Okay, so that is by dtl, pi dtl we can do 2 pi r. Okay, 2 pi r times length is the cylinder surface area, so that we can write. So b times pi dt lt. Okay, so that will be the q dot. So yeah, if you rearrange the terms, you can find an expression for theta out. Now, sixth question. In the radiator of a diesel generator set, hot coolant from the engine enters at the temperature theta c, comma inlet degree centigrade. So C is for coolant, I guess. And after being cooled, it exits at temperature theta c, comma out. The coolant mass flow rate is m dot c, kilogram per second. Calculate the heat transfer rate from the coolant. Okay, so again the same formula. So m dot h out minus h in, we will be thinking about that. Q equal to m dot h out minus h in. Instead of that, we will be thinking m dot cp theta out minus theta in. Okay, and then so it is cooling means like inlet will be having higher temperature than outlet, so in that manner you have to use the sign convention. Yeah, that's it. Then question number 7. Question number 7 is a block of aluminium of mass A. One second. A block of aluminium of mass Ma at temperature theta A is brought in contact with another block of aluminium whose mass is Mb and temperature is theta B. There is no heat transfer from either block to the surroundings. Write the expression for the final state properties in terms of given parameters. Okay, so Q, temperature lost by A equal to Ma Cp. So both are coming to a common temperature that I'll take it as theta final, and initial temperature of A is theta A. Okay, so here also Qb equal to Mb Cp. So common temperature is theta final minus theta B. Okay, so if you can equate Qa equal to Qb. Okay, that's it. So theta final will be MA theta A. It's of same material, so CP will be constant. It will be like um, cancelling out. So only MA, MB, theta A, theta B will be left. So you can find an expression for theta final in terms of theta A, theta B, and MA and MB. Okay, that's it. Then question number 3.8. Second, we'll just keep it over here so that the confusion won't be there. A device has two chambers connected by a pipe with a valve. The device is well insulated. One chamber has volume VA meter cube and the other has volume VB meter cube. Initially in state 1, chamber A is fully evacuated and the other chamber B is filled with MB kilogram of a substance at pressure phi B1 bar and temperature theta B1. The valve is opened and the system attains equilibrium at a new state, state 2. The final pressure phi A2 and equal to phi B2 and final temperature theta A2 equal to theta B2 are desired. Give the calculation process for this purpose. Alternatively, give two independent properties in the final state that can be calculated from the above data. Okay. Okay. So what they are saying is there is no heat and mass exchange outside. So it is well insulated. Sorry, well insulated and it is closed, right? So no heat and mass exchange outside. So the total mass after the mixing is MB. Okay. Total mass is going to be MB kilogram. Final volume is going to be volume of chamber 1 plus volume of chamber 2. VA plus VB. Okay. So energy conservation, if we are considering well insulated uh, like chamber and no work is done and etc., then delta U equal to 0. Okay. So mass equal to MB, V equal to VA plus VB, and delta U equal to 0. Final state, final pressure phi2 and temperature theta 2 must be found using U final equal to U initial. Okay, 1 second. One second. One chamber has VA volume and another chamber has VB volume. Chamber 1A is fully evacuated and the chamber B is filled with MB at pressure phi B1 and temperature theta B1. The valve is opened and the system attains equilibrium at a new state, state 2. Final pressures are phi A2 and phi B2. Final temperatures are theta A2 equal to theta B2. Okay, fine. So we have to, so delta U is going to be constant. That means U1 equal to U2. Okay, U1 equal to U2. So U1 is what? Initially also mass was MB U of theta B1. Okay, that was the initial temperature equal to MB U of theta B2. because okay. So this is the expression for calculating the properties. Theta b1, if you know, then we can find theta b2. Okay, then from there, from PVT relationship, you can find phi a1 and phi a2, etc. Okay, ideal gas law, we can find pressure. Now, ninth question. Fluid is flowing in a pipe. A fluid is flowing in a pipe, and its temperature is theta 1 degree centigrade and pressure is phi 1 bar. It passes through an expansion valve, after which its pressure drops to phi 2 bar. The inlet and outlet velocities are comparable. The device is placed horizontally from inlet to outlet, which two independent properties at the outlet fully define the outlet state. Okay. So for expansion valve, so expansion valve is also known as throttling valve. So it is steady state process with no heat exchange, and there is negligible kinetic and potential energy, no shaft work. So expansion valve, the equation is what? Expansion valve, we will be taking H inlet equal to H outlet. That is how we are considering. So pressure at outlet is phi 2, and enthalpy at outlet equals inlet enthalpy. So two independent properties are pressure and enthalpy, specific enthalpy. Okay. Okay, so this is how we'll be defining. These are the two independent properties that we need to know. Then for a throttling device. Then the 10th question. Air is compressed and then passed through a heater as shown below. Compressed work is WC and heater electric power is Q dot H. Assuming steady state and delta Ke equal to delta Pe equal to 0 and steady state prevails, which of the following is correct for the system shown below that includes only air in the marked space? Okay, so there were options given. So these are the options. One second. So air is compressed and then passed through heater. Okay, so from compressor to heater. And diagram is state 1. State 1 is inlet of compressor, state 2 is inlet of heater, and state 3 is outlet of heater. Compressor work is WC and heater work is WH. WC and WH. Fine. Steady state delta K equal to delta P equal to 0. Fine. So we have to write the equation for the whole system. So M dot H1 is the inlet enthalpy plus WC is the work of compressor plus WH is the work of heater equal to outlet enthalpy. This is the equation, right? KE, PE, everything is gone. Q is not there. Okay, rearranging, we will be getting WC plus WH equal to M dot H3 minus H1. Okay, now we have to compare with the options. So this will be equal to option A, like WH equal to minus WC plus M dot H3 minus H1. This is the answer, right? So A is the correct answer. Yes, so that's all for today. We have discussed the week 3 assignments and revision questions. If there is any doubt, please let me know in the messages. I'm concluding the class for today. Thank you.